Good day everyone and welcome to our next lesson. In this video, we'll be talking about interface mass transfer or the transfer of mass between two distinct separate phases. Let's begin. Interface mass transfer is the transfer of a chemical species from one phase to another, and it has been widely studied due to its vast applications such as absorption, leaching, and extraction. Basically, these are separation techniques that are being used in some processes in order for us to either separate substances or combine substances. For the study of interface mass transfer, several equations are of utmost importance. The first is we will be assuming that the liquid phase is ideal, thus Rolle's law applies. Rolle's law simply states that the partial pressure of substance A over a liquid is equal to the mole fraction of that substance multiplied by the vapor pressure of that substance. As such, if you have a pure substance, x sub A is equal to 1 or the mole fraction is equal to 1. Thus, the partial pressure over the solution is equal to the saturation vapor pressure. Another equation that we will be using is Dalton's law, and this applies if the gas phase is considered ideal. Dalton's law states that the partial pressure of a substance A in a mixture of gases is equal to the mole fraction of A on that mixture of gases multiplied by the total pressure P sub T. In order for us to reduce ambiguation, we will be using X to denote mole fraction in the liquid phase and Y for the mole fraction in the vapor or gas phase. Okay? That is the distinction between X sub A and Y sub A. If you notice, we can actually equate Rolle's law to Dalton's law and we will get a special relationship. This is at equilibrium. We have the mole fraction of A in the liquid phase multiplied by its vapor pressure is equal to the mole fraction of A in the vapor phase multiplied by the total pressure. This relationship is useful for determining the mole fraction of any substance either in the vapor phase or in the liquid phase, assuming that both the liquid and the vapor phase are ideal. Another useful relationship that we will be using is the Henry's law. Henry's law states that the partial pressure of a certain species on the gas phase is directly proportional to its concentration in the liquid phase, and the constant of proportionality is called H, or the Henry's law constant. This is applicable for the dissolution of gases, wherein if you have a high partial pressure of a substance over a solution, then you will also have a high concentration in the liquid phase. Okay? We will be using all of these equations in our examples. Let's try this example. An exhaust steam from a semiconductor fabrication unit contains 3 mole percent acetone and 97 mole percent air. In order to eliminate any possible environmental pollution, this acetone air stream is to be fed to a mass transfer column in which the acetone will be stripped by a countercurrent falling 293 Kelvin water stream. The tower is to be operated at a total pressure of 101,325 pascals or atmospheric pressure. If the combined Rolle-Dalton equilibrium relation may be used to determine the distribution of acetone between the air and the aqueous phases, determine the mole fraction of acetone in the aqueous phase in equilibrium with the exhaust steam. Here we have our given to the problem. So we have a falling liquid phase, which is water, and we have a rising gas phase, which is 3 mole percent acetone and 97% air. If we will denote acetone as letter A, then we say that Y sub A is equal to 0.03. This is the mole fraction of acetone in the gas stream. While for the liquid stream, we say that X sub A is the unknown because we want to know what is the equilibrium concentration of acetone in water that is in contact with air containing 3% acetone. For this problem, we will be using both the Rolle's law and Dalton's law because the Rolle's law pertains to the liquid side and the Dalton's law pertains to the gas or vapor side. So let's write Rolle's law as the partial pressure of A, which is acetone, is equal to the mole fraction of acetone in the liquid phase multiplied by the vapor pressure of acetone. Next, we write Dalton's law. The partial pressure of A is equal to the mole fraction of A in the gas phase multiplied by the total pressure. Equating the two equations, we have X sub A vapor pressure is equal to Y sub A total pressure. Solving for X sub A, we have Y sub A total pressure over vapor pressure. Now, before we can evaluate this expression, we first need to determine the vapor pressure of acetone at 293 Kelvin. For the vapor pressures, we can turn to our handbook to determine the values. We have table 2-8, the vapor pressure of inorganic and organic liquids in the following equation. You can use either this table with this equation, or you can use the Antoine equation, provided that you are given the constants to the Antoine equation. Okay? The Antoine equation is simpler because it only contains 3 parameters, and this equation in our handbook contains 5 parameters. So for acetone, we have here the values of C1, C2, C3, C4, and C5. You simply substitute those in this equation, and then you will be given the vapor pressure in pascals. Calculating, we have the vapor pressure at 293 Kelvin, 24,353.32 pascals. We can now use this vapor pressure to substitute in our equation for mole fraction in the liquid phase. Substituting, we have Y sub A, that is 0.03. This is the mole fraction of acetone in the gas phase, multiplied by the total pressure, 101,325, divided by the vapor pressure, 24353.32 pascals. The mole fraction of acetone in the liquid phase is 0.125. This result tells us that 0.125 is the equilibrium mole fraction of acetone in water, and that is in conjunction with the 3% acetone in the vapor phase. These are the mole fractions in the liquid and the vapor phase in equilibrium. So if we are reading values that are less than these mole fractions, we will be certain that the system is not yet at equilibrium. Okay? Let's proceed. This is a Henry's law problem. The Henry's law constant for oxygen dissolved in water is 4.06 times 10 raised to 9 pascals per mole of O2 per total mole of solution at 293 Kelvin. Determine the solution concentration of oxygen in water that is exposed to dry air at 101,325 pascals and 293 Kelvin. Here are our given to the problem. So you're given the Henry's law constant, 4.06 times 10 raised to 9 pascal per mole O2 per mole solution. You're also given the temperature and the total pressure. Now, the first thing to recognize when using Henry's law is that there are several forms of the Henry's law equation that we can use. And all of those forms are different with the way on how we express either concentration or partial pressure. The form of the Henry's law equation will depend on the units of the Henry's law constant. In this case, our Henry's law constant has units of pascals per mole O2 per mole solution. Essentially, our denominator is simply a mole fraction. This gives us an idea that our denominator is expressed in terms of X, or the mole fraction in the liquid phase. While our numerator is a unit of pressure, that's why we can infer that it is expressed in terms of partial pressure. Therefore, for this instance, we can write our Henry's law as PA, or partial pressure of A, is equal to Henry's law constant multiplied by X sub A, or the mole fraction of A in the liquid phase. This is very important because this plays into the homogeneity of the units of our Henry's law. Okay? Other forms of the Henry's law include Y sub A is equal to H times X sub A, wherein both the liquid and the gas concentrations are expressed in terms of mole fractions. We can also have Y sub A is equal to H times C sub A, or we have mole fraction in the gas phase and molar concentration in the liquid phase. Or we can also have both partial pressure and molar concentration in the same equation. So the determination of the form of the Henry's law equation will rely on the units of the Henry's law constant. Okay, let's proceed. We are tasked to solve for X sub A in this case. So rearranging our equation, we have X sub A is equal to P sub A over H. Before we can solve this, we first need to determine the partial pressure of oxygen in air. Now, our total pressure is 101,325 pascals. A simple way of determining the partial pressure is through the use of the Dalton's law equation. That is, partial pressure is equal to mole fraction multiplied by the total pressure. And we all know that dry air can be approximated using two components, that is oxygen and nitrogen, wherein oxygen is 21 mole percent and nitrogen is 79 mole percent. Therefore, we know that Y sub A is equal to 0.21. Substituting this into our XA equation, we have YA times the total pressure over the Henry's law constant. If you take a look at the cancellation of units, in the numerator, your unit is Pascal. In the denominator, the unit of H is Pascal per mole fraction. Pascal cancels, and you will be left with mole fraction. Substituting, we have 0.21 multiplied by 101,325 divided by our Henry's law constant 4.06 times 10 raised to 9. Our mole fraction, x sub A, is equal to 5.24 times 10 raised to negative 6. This mole fraction of oxygen in water is what we call the maximum allowable concentration of dissolved oxygen in water, or the saturation concentration of dissolved oxygen. This saturation concentration decreases as your temperature increases. That's why as the temperature increases, there is less and less dissolved oxygen in the water. Actually, the same is true for almost all gases, wherein if you increase the temperature, your saturation concentration will be much lower. Okay, this is how we use Henry's law. Let's go back. Now let's dive into the interface mass transfer itself. For the visualization of interface mass transfer, we have here two films, the gaseous film and the liquid film. Assume for a moment that our liquid film is falling in this case and our gaseous film is rising. This gives a countercurrent contact between the two phases. Let us first take note of the important parts of this system. We have the gas-liquid interface wherein the gas and the liquid films meet. We have the bulk gas and the gas film, and we also have the bulk liquid and the liquid film. Now, in order for us to understand this interface mass transfer, we first have to realize that both diffusion and convective mass transfer are at work in interface mass transfer. The gas film and the liquid film are both called the boundary layers. In the boundary layers, diffusion accounts for majority of the mass transfer. That means that in the boundary layer, we are encountering the slowest rate of mass transfer. That's because we are relying on diffusion to transfer a species from one point to the other. If you go past the boundary layers of both phases, we have here the bulk liquid and the bulk gas. In both of the bulk phases, we are assuming that convective mass transfer accounts for a large part of the mass transfer. So if you will take a look at our direction of mass transfer, assume for a moment that we are transferring species A from the bulk gas to the bulk liquid by contacting the liquid with the gas. What happens first is species A is being transferred in the bulk gas, and it is being transferred as well in the gas film due to diffusion, such that the driving force of the diffusion in the gas film is PAG minus PAI, wherein PAG is the partial pressure of species A in the bulk gas, and PAI is the partial pressure of A in the interface. Remember that the interface is the boundary between the gas and the liquid phases. Now, the interface mass transfer happens in this interface. Our driving force in this case is PAI, or the partial pressure of A in the interface, and the concentration of A in the interface. If you will notice, we can relate PAI and CAI with the use of Henry's law. That's why we needed to discuss Henry's law, because that is the equation that we will be using in the interface. Okay? And then after the interface mass transfer, there is now a concentration gradient of A. So we are now transferring species A across the liquid boundary layer with the concentration gradient of CAI, or the concentration of A at the interface, minus CAL. Sorry, this should be CAL. That means that this is the concentration of A at the bulk liquid. And we have here our Henry's law relationship. PAI is equal to H times CAI, wherein H is our Henry's law constant. This is applicable in our gas-liquid interface. Okay? If we take a look at the graphical representation of the partial pressure of A in the gas phase versus the concentration of A in the liquid phase, we see here an equilibrium curve. For every point touching this equilibrium curve, we can apply Henry's law. That's why you see here that CAI, or the concentration of A in the interface, intersects with the partial pressure of A in the interface in our equilibrium curve. That means that your Henry's law constant can be used here to convert from PAI to CAI, or from CAI to PAI. Okay? Our point O here is called the operating point. If you take a look at the coordinates of our operating points, we have PAG, or the partial pressure of species A in the bulk gas, and we have CAL, or the concentration of A in the bulk liquid. Okay? So what is our effective driving force here? We have two types of driving force, first on the gas side and second on the liquid side. On the gas side, the driving force is PAG minus PAI, and on the liquid side, our driving force is CAI minus CAL. And if you remember our general equation for molar flux, Our molar flux is characterized as driving force over resistance. In the case of interface mass transfer, our flux is NAZ, our driving force is PAG minus PAI, and our resistance is 1 over K, in which K is the mass transfer coefficient. If you rearrange that equation, we have the overall flux equation, that is molar flux of A along the z direction is equal to the mass transfer coefficient Kg, G signifying that the mass transfer coefficient is for the gas side, and we have the concentration difference PAG minus PAI. On the liquid side, we can also write that as negative KL. KL is the mass transfer coefficient on the liquid side multiplied by the driving force CAI minus CAL. Now, if we draw a line from the operating points up to any point in the equilibrium curve, the slope of that is the ratio of the mass transfer coefficients. Mass transfer coefficient for the liquid side over mass transfer coefficient on the gas side. Okay? So please remember this overall flux equation. However, the problem with using these flux equations is that we are only using one side of the interface mass transfer at a time for our equations. If you use this first half of the equation, you're only considering the gas phase. And if you consider the second equation, you're only considering the liquid phase. Now, to reconcile that, we have here another set of flux equations in which we are now using overall mass transfer coefficients. If you take a look at the mass transfer coefficients, this time our mass transfer coefficients are in capital letters. Capital letters will signify that these are overall mass transfer coefficients. Our flux equation now becomes Kg, or the overall mass transfer coefficient for the gas side, multiplied by the driving force PAG minus PA asterisk. Now, what is PA asterisk? PA asterisk is what we call a fictitious partial pressure of A. The fictitious partial pressure of A accounts for the total driving force of the system. That means that PA asterisk now includes the driving force in the liquid phase as well. Okay? Such that if we get the difference PAG minus PA asterisk, we are really talking of the driving force PAG minus CAL. That gives us control over the entire interface mass transfer problem from the gas phase to the liquid phase. The same is true for the second half of the equation. We have here the overall mass transfer coefficient using the liquid coefficients multiplied by the overall driving force, Ca asterisk minus Cal. Ca asterisk also accounts for the driving force including the gas phase. Such that if we take Ca asterisk minus Cal, what we really are saying is we are using the driving force PAG minus Cal. Okay? And you can only do that with an overall mass transfer coefficient. Now, the question now is, how do we convert our individual mass transfer coefficients to our overall mass transfer coefficients, since we have proven here that overall mass transfer coefficients are more flexible and are more useful. Here are our equations for converting individual film transfer coefficients to overall mass transfer coefficients. The first equation, 1 over capital Kg, is equal to 1 over small kg plus m over small kl is our equation for the determination of the overall mass transfer coefficient in the gas side, while the equation below dictates how we determine the overall mass transfer coefficients in the liquid side. Okay, if you will notice, these equations are written in terms of resistances because 1 over kg gives us the overall resistance to mass transfer. That is also true for 1 over capital KL. Okay, and finally, we can also determine the contribution of the resistances using these equations. The percent resistance from the liquid side is capital KL over small kl, and the percent resistance from the gas side is capital Kg over small kg. By doing this, we can determine which phase is contributing more to the resistance such that we can optimize the process. For example, if we have determined that 95% of the resistance is coming from the liquid side and the remaining 5% is from the gas phase, that means that we have to improve our individual transfer coefficients in the liquid phase such that we can have a faster interface transfer of the species. Okay, that is how we use these equations. Let's try to solve some examples. In an experimental study of the absorption of ammonia by water in a wetted wall column, the overall mass transfer coefficient Kg was found to be 2.74 times 10 raised to negative 9 kilomole per square meter per second per Pascal. At one point in the column, the gas phase contained 8 mole% ammonia, and the liquid phase concentration was 0.064 kilomole of ammonia per cubic meter of solution. The tower operated at 293 Kelvin and 101.325 pascals. At that temperature, the Henry's law constant is 1.358 times 10 raised to 3 pascal per kilomole per cubic meter. If 85% of the total resistance to mass transfer is encountered in the gas phase, determine the individual film mass transfer coefficients in the interfacial compositions. Here are the given to the problem. So we have a liquid and gas interface, and mass is being transferred from the gas to the liquid. We are transferring ammonia, and the concentration of ammonia in the gas is higher than the concentration in the liquid. In the gas phase, the mole fraction of ammonia is 0.08. That is our YAG. We are also given the concentration of ammonia in the liquid stream. That is our CAL. That is 0.064 kilomole per cubic meter. If our total pressure is 101.325 pascals, we can simply multiply that with 0.08, which is the mole fraction of ammonia, to determine the partial pressure of ammonia in the gas phase. That is 101.325 multiplied by 0.08, 8,106 pascals. That is the partial pressure of ammonia in the gas phase. At this point, we can now determine the overall flux of ammonia, that is N sub A. If we go back to our formulas, we can use this molar flux equation that is expressed in terms of the overall mass transfer coefficient. Since we are already given the value of capital Kg, we can use the first half of this equation to determine the mass flux. We are doing this because we are asked to solve for the interfacial concentrations, and by solving for the molar flux, we can then later solve for the interfacial concentrations. Okay? With our molar flux equation, Na is equal to capital Kg multiplied by the driving force PAG minus PA asterisk, we have to define what is PA asterisk. Now, for the fictitious concentrations PA asterisk and Ca asterisk, we can express them in terms of either pressure or concentration with the use of Henry's law. With this, we write that PA asterisk is simply equal to the Henry's law constant multiplied by the concentration of ammonia in the bulk liquid phase. Doing so allows us to substitute PA asterisk into our above equation such that we get a flux equation Na is equal to capital Kg multiplied by PAG minus H times CAL. We now have all of our given to be substituted here. So let's substitute. Capital Kg is 2.74 times 10 raised to negative 9 kilomole per square meter per second per pascal. Multiply that with PAG, that is 8106 pascals, minus H times CAL. H is 1.358 times 10 raised to negative 3, multiplied by CAL, 0.064 kilomoles per cubic meter. Our molar flux Na is equal to 2.22 times 10 raised to negative 5. Take a look at the cancellation of units. The terms inside of the parentheses have a unit of pascals because those both pertain to partial pressures. And then if you multiply pascals with kilomole per square meter per second per pascal, the units of capital Kg, you will be left with the usual units of flux, that is kilomole per square meter per second. We have now determined the molar flux of ammonia in the system. Now, this determination of the molar flux allows us to determine the interfacial concentrations by the use of the same molar flux. We can write now our equation molar flux in terms of interfacial concentrations as small kg multiplied by the driving force PAG minus PAI. If you take a look at our diagram here, this is PAG, this is PAI. PAG is greater than PAI, so that becomes our mass transfer gradient. Okay, that is PAG minus PAI. This molar flux is also equal to small kl multiplied by CAI minus CAL. Now, our driving force for the liquid side is CAI minus CAL because CAI is higher than CAL. And now that we have the value of Na or the molar flux, we can simply substitute that into either half of the equation to determine the interfacial concentrations. However, we first need to determine the individual mass transfer coefficients small kg and small kl before we can substitute them into this equation. These are the equations that we will be using for the conversion from the overall mass transfer coefficient on the gas side to the individual mass transfer coefficients. Let us first exploit one of the given that says that 85% of the resistance is coming from the gas phase. Therefore, we can use the last equation here in order to convert from the overall mass transfer coefficient in the gas side to the individual mass transfer coefficients in the gas side. For that, we write that 85% of the resistance is equal to capital Kg over small kg. Since we know the value of capital Kg, we can now determine the value of small kg, and that is 2.74 times 10 raised to negative 9 divided by 0.85. Our individual mass transfer coefficients on the gas side is equal to 3.22 times 10 raised to negative 9, and this has the same units as the overall transfer coefficient, that is kilomole per square meter per second per Pascal. Now that we know the value of our film transfer coefficients on the gas side, we can now determine the other individual mass transfer coefficient using the conversion equation 1 over capital Kg is equal to 1 over small kg plus m over small kl. Now you might be wondering, what is this m in this equation here? The m in this equation represents the slope of the equilibrium curve. If you take a look at this graph, you can see that our equilibrium curve is a curve, no? It is not a straight line. However, we can approximate that the slope of this equilibrium curve in this point here wherein the operating point intersects with the equilibrium curve as the Henry's law constant. Okay? So in short, you can simply replace m, or the slope of the equilibrium curve, with h, or the Henry's law constant. We can now replace our m with our Henry's law constant. Since we were given the overall mass transfer coefficients and we have determined the individual film transfer coefficient for the gas side using the percent resistance equation, we can now solve for small kl. And that is simply 1 over capital Kg, 2.74 times 10 raised to negative 9, minus 1 over small kg, that is 3.22 times 10 raised to negative 9. And then we can raise this to negative 1 so that we can invert this fraction. What we will have is 1.838 times 10 raised to negative 8 is equal to kl over h. To make this equal to kl, we simply multiply this by the Henry's law constant, 1.358 times 10 raised to 3. Our liquid side mass transfer coefficient is 2.50 times 10 raised to negative 5. Now, what is the unit of this K sub L? Earlier in our lesson in convective mass transfer, we have determined that the units of small kl, or the mass transfer coefficients on the liquid side, is meters per second. We can verify these units by taking the ratio of the units of kl and the units of the Henry's law constant. So kl has units of meters per second, and then Henry's law constant has units of pascals per kilomole per cubic meter. And if you simplify this, we should end up with the same collection of units as capital Kg. So what will happen here is meter will cancel with cubic meter, leaving us with square meter. And this would simplify as kilomole per square meter per second per Pascal. This is the same collection of units as capital Kg. Okay, so please do take note of the units of the individual mass transfer coefficients because they are different for the gas side and for the liquid side. So now we have determined the values of the individual mass transfer coefficients. We can now use this equation to determine our interfacial concentrations. Again, our governing equation is Na is equal to small kg multiplied by PAG minus PAI is equal to small kl multiplied by CAI minus CAL. We can now substitute everything in these equations and solve for PAI and CAI. Let's first solve for PAI. So for PAI, we are using the gas side of the equation. That is the first half of the equation. That would be Na, or 2.22 times 10 raised to negative 5, divided by small kg, or 3.22 times 10 raised to negative 9. This is now equal to the driving force PAG minus PAI. To solve for PAI, we simply subtract this value from our PAG. Our PAG is 8106 pascals. Subtracting the answer from earlier, our interfacial partial pressure of A or PAI is 1212 pascals. Next, for CAI, we simply use the right-hand side of the equation, which deals with the liquid side, that is Na, 2.22 times 10 raised to negative 5, divided with small kl, which is 2.5 times 10 raised to negative 5 meters per second. And then this ratio is equal to CAI minus CAL. To solve for CAI, we simply add this to CAL. So we add 0.064 kilomole per cubic meter. Our concentration in the interface is 0.952 kilomole per cubic meter. Okay, and that is how you approach problems of interface mass transfer. Now, the other variations to problems involving interface mass transfer will just be asking you to solve for other parameters. Maybe for other problems, the given are the individual mass transfer coefficients, and you are asked to solve for the overall transfer coefficients or the molar flux of A. In any case, you simply have to use the formula that are given in this video, and those equations are the molar flux equations for the interfacial concentrations and for the fictitious concentrations, as well as our equations for converting from individual film transfer coefficients to the overall mass transfer coefficient, as well as the percent resistance. Okay, that's all for this video. I hope you have learned something. Thank you for listening, and as always, keep safe.